BFS, how the roots or nodes are, how nodes are traversed from the root. So here in BFS, the nodes are divided into the levels. In different levels, different nodes are present. So one by one level, you have to visit all the nodes. So this visiting all the nodes requires more space in BFS. And the space required for DFS is order of D, where D is the depth of the tree, but the space required by BFS is order of N, where N is the number of nodes. So number of nodes will be much more in a particular level than the levels in a tree or a graph. So these two BFS and DFS algorithms have some limitations. That's why we will now see iterative deepening search algorithm. Let me just share with you. Just a minute. You can see here, I've discussed about the DFS and BFS, how these both are not very much efficient for traversing a node. Now we will come to iterative deepening search. Here I have taken one example, even C, a tree having 4 levels from level 0 to level 3. And the nodes are, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 15. So we are going to search for the goal node 15. We can write like this: depth or level in one side, and ideas means iterative deepening search in the right hand side. First we will start with level 0. So the root node is 1, so we'll write 1. Then at level 1 we will move towards the next level. Here you can see directly it will take the root 1, then 2, 3. It will move like this. It will move just like this way, and again first this will move like this. Then before moving here, it will go towards up again. Then it will move towards right. So like this, you can see one by one nodes are visited, and we will write here. At last, we will get the result like this. after visiting all the levels. Just see the example once. So both BFS and DFS technique is used in IDS. You can clearly see from this. So depth also, it is in all the depths the nodes are visited, and level wise also the nodes are visited. So both techniques are used in IDS. We have seen in this example. So this we have seen how IDS is used. So the comparison table between DFS, BFS, and IDDS means iterative deepening search depth first search. We can say like that. We have written here, you can see DFS as time complexity is order of B to the power D, space complexity is order D. And when we have to use it, if uh, the node we are going to visit is closest to the starting node, then we can use DFS, or when the graph or tree is not very big or infinite. So in that case, we can use DFS. And also, I've written this as B to the power D. B is your branching factor, means the average number of child node each node is having, and D is the maximum depth of search tree. So DFS explores every possible path to its max depth, means towards downside before backtracking. And in worst case, DFS explore all nodes down to the max depth D. So for B and D, total number of nodes in a complete tree is approximately written as b to the power 0 plus b to the power 1 plus b to the power 2 plus up to b to the power d. So the time complexity for DFS will be order of b to the power d, as most nodes are at deepest level. So we visit all the nodes towards left hand side, and it will go deep, and all the nodes are visited. Then the space complexity is order of d. So only current path is stored in memory at a time. And the maximum number of nodes in current path is equal to depth of tree d from root to the current node. Then for BFS, the time complexity is written as order of b to the power d, same as the time complexity of DFS. As in BFS, nodes are explored level by level. So I have discussed in the previous examples also how BFS and DFS are together both used in IDS. In BFS only, uh, it starts from the level 1, and you can write that level as level 0, where one node will be there, so it will be visited. Then at uh, depth 1, B number of nodes say are there, so they will be visited. And in the second depth, b to the power 2 nodes are there, so they will be visited till up to uh, depth d. B to the power d nodes will be visited. Then in worst case, BFS explores all the nodes at all depths up to d. Similar to like in the order of DFS, BFS also we can write order of b to the power 0 plus b to the power 1 plus b to the power 2 plus up to b to the power d. So order of b to the power d will be the time complexity of BFS, but it will be traversed in at the level wise. But all the nodes will be visited at all the depths. Then the space complexity is order of b to the power d. So in BFS, it uses Q to store nodes at current level, and in worst case, Q stores nodes at the deepest level b to the power d. So the order of b to the power d will be the space complexity as it stores all the nodes at maximum depth level at once. So all the nodes in a particular level are stored directly at a particular level. Then we can write as order of b to the power d as all the nodes are stored at a particular level. So this will be the space complexity for BFS. And when BFS you can use uh, when the space is not a very issue. As you can see that order of b to the power d is much more space consuming as all the nodes have to be visited at a particular level. So it will take more space for all the nodes for visiting. And when the goal node is closest to the root node, then in that case also we can use BFS. For iterative depth first search, the time complexity is order b to the power d. So it's similar to BFS as majority of the nodes are at the deepest level d. The number of nodes in a tree as b to the power 0 plus b to the power 1 plus b to the power 2 up to b to the power d. But the earlier iterations we explore upper levels. So final iteration will be order of b to the power d. So it is just similar to BFS, how the BFS nodes are visited at level wise. But in depth wise also we are moving for visiting the nodes. So then we can write time complexity of IDDFS as order of b to the power d. And for space complexity, we can write order of b into d. So like DFS, IDDFS is depth limited at each iteration, means it will only stores the current path explored. So space complexity of DFS for each iteration is order of d, but in IDDFS, it performs DFS for each depth level. So in worst case, when a graph is searched, space complexity will be order of b into d, which will be higher. So it will use both BFS and DFS for iteration. Next, moving on to informed search. So earlier we were learning about uninformed search. So in informed search, we will see two types of algorithms: greedy best first search and A star search. So what is informed search? So informed search algorithms have already the pure information about the goal state, means which node we have to visit. So that information we already have, which helps us in efficient searching. So this information we call as heuristic. So in informed search, heuristic is a function denoted by hn estimates how close a state is to the goal state. So it will be already known to us as heuristic function in informed search, so that we can reach the goal state uh, using the heuristic function. So it will hn is the estimate of the distance of node n from the goal node. So in greedy best first search, the lower the value of hn, closer is the goal node from the goal. This we will see with an example. So this is an example how greedy best first search algorithm can be used. Uh, we can see here a roadmap of Romania. So there are different places which are connected as a graph. You can see, and this distance to Bucharest is written here. You can see at 366, Bucharest is zero only because it has to be visited. So these distances from various places are already given. So it will be your hn heuristic function, and we can also denote it as fn equal hn, estimate of total cost from n to goal. So how we can use greedy best first search for this particular roadmap. And these are the actual distance. So it is only the estimated distance it's mentioned here. And this will be the actual distance. And these distances are the direct straight line distance from this place to Bucharest, from this all the place to Bucharest. So these are all written here, and these are the actual distance how uh, from this place to this place all distances can be covered. It can be by road in various types of routes. It can be reached. So this type of distance is written here, and these are the all straight line distances directly to Bucharest. So how we can use this informed greedy best first search? I will just share. You can see how greedy best first search algorithm can be used for this example. We were talking about the heuristic function. So fn or hn, we can write fn equal to hn is given as 366 as the straight line distance to Bucharest. From Arad to Bucharest, it's 366. Then Sibiu, it's given as 253. Likewise, it is already given in the example. And all the actual path cost so far from start node to the current node can be denoted as gn. As I've already told that the actual distance is written there. It's somewhat different. You can see. Here you can see. So gn here it's mentioned. Here gn will be not used. Here in database first search only fn equals to hn will be used, which is already here you can see. So first we are taking this place Arad. So Arad we are writing, and the adjacent nodes are this Sibiu, Timisoara, and Zerind. So the HN for all these three are written: CPU 253, Timesora 329, Zerint 374. Then what you can see, the least value is 253 among all the three fringes. We call this as fringes. So this will be the least. So we will consider this one here. And again, we will take the adjacent places to CPU. Here from the map, you can see Rimnishu, Vilcia, then Fagaras, then Oradia, and Arad also are the adjacent places to Sibiu. So it's already given 366 Arad. Fagaras is 178. From here you can see Fagaras is 178. Oradia is 380. 380. Then Rimnishu Vilcia is 193. So here we will write all this, and again we will see which is the least value here of HN. 178 is the least among all the four, so we will consider this, and again we will take the adjacent places to Vagaras. Vagaras adjacent places are Sibiu and Bucharest. So only two places are there, Sibiu 253 and Bucharest 0. Now we will reach Bucharest. So in this way we will reach our goal node. You can see from this example. So in like this we can use greedy best first search, and it is called as informed search technique, as the HN heuristic function is given as the estimated distance to the goal node. Just see the example. Okay, now we have seen how greedy best first search can be used. We'll move on to next technique, informed search, uh, A star search in informed search. So another technique we will see here. Here one another function will be used for evaluating. Function of n will be equal gn plus hn. Gn is the cost so far to reach n, and the hn is the estimated cost from n to goal, which we have already seen in the previous technique. And fn will be the estimated total cost of path through n to goal. So these two values will be combined to get the estimated total cost of the path to the goal. And this technique is chosen as an admissible heuristic that never overestimates the cost to reach the goal. Means it's an optimistic technique, and it's due to its completeness and optimality. How? Or it always finds a solution if one exists. if search space is finite and cost to reach the nodes is non-negative. So it is always complete, and it's optimal when using a heuristic. Since heuristic is a algorithm does not overlook the optimal solution. The lowest estimated total cost expands leading to find the shortest path to goal. When Hn is admissible and cost of Gn is non-negative, then it's optimal. So due to these factors, it is considered as optimistic. So how it can be used, we will see in our example. Here, other example is there. You can see same roadmap of Romania, but how A-star search can be used. You can see here. Just like the greedy base first search, we will write first Arad, then its adjacent places Sibiu, Timisoara, Zerind. But as we have seen that the function of n will be gn plus hn, so we will write as 140 is your gn. It's mentioned here as I have already told you. It's 140 from Arad to Sibiu, and Sibiu it's given 253 as heuristic function hn. You can see 253. So combining both, we will get 393. Then similarly for Timisoara and Zering, we will find out the Fn by combining the two values. Just like greedy best first search technique, we will consider the least value, which is 393 among all the three places given. So we'll consider Sibiu. Then for Sibiu, what are the adjacent places? You can see from here. Arad, then Fagaras, then Oradea, Rimnishu, Vilcia. So these all are the adjacent places of Sibiu. Similarly, we will calculate the Fn by combining Gn and Hn values. We will get 646 for Arad. Uh, how 643, how 646, how it's 280. You can see that we have already find out the we have already have the gn value of 140 from Cebu to Arad. So this 140 will previous value will be used, and again this value will be combined with this value, so we'll get together 280. So we'll write 280 here, and then we'll directly write hn value of Arad 366, and we will combine all these values to get 646 Fn value. Similarly for Fagaras also we will write like this: 239, how we'll get that value 239, 140 you have already got here. So this will be combined with the value 99. So 140 plus 99, you will get 239, and combine the value of HN, which is 178 for Fagaras, and combining all these values, you will get 417 for Fagaras. Similarly, we will calculate for Oradea, Rimnishu. So out of all these four values, 646, 417, 671, and 413, which will be your lowest value here. 413 is the lowest value. So we'll consider again this value, Rimnishu Vilcia. So we'll again write the adjacent places of this place, Rimnishu Vilcia, Craiova, Pitesti, Sibiu. And Similarly, we will find out the value of fn by combining gn and hn values from the previous values and the given values. We'll get these values for all the three places. Now we are getting, in this level, we are getting five different places with their values. So among all these, you can see 415 is the lowest. Now we will consider Ptsd here. We will again write the adjacent places: Bucharest, Craiova, Râmnicu, Vilșia. So similarly, we will determine all the values of Fn from the values we will be using from the above and from the given values. We will get the values for each of these places as 418, 615, and 607. Now we have reached the place Bucharest, which we have to find out. We are getting the value 418, but in our memory, lower value is there, which we have not visited, which is 417 for Fagares. So this fringe is having lesser value from this. Now we will see how uh, what is the value we can find out to get the value of Fn for Bucharest. So we will consider again here Fagares, Sibiu, and Bucharest. These are the adjacent places of Fagares. So we will use similar type of way to find out the value of Fn. We will get 591 for Sibiu and Bucharest will get 450. As Bucharest to Bucharest is 0, here it's mentioned already. So finally we will get these values for all the fringes. And we have reached Bucharest here. So here you can see we are getting 450 and here we are getting 418. So the list will be your 418 only. So this will be, we will consider as the least distance as, or the least cost to reach the place Bucharest. Just see the example once, then we will move on to next slide. Any doubt till now?
What is the difference in optimality between the
Any question?
sir difference between the two, sir, in application?
Application difference is just here we will consider the GN values in your A star search, and in the greedy base first search we will only consider the heuristic values. So the both are different from each other.
Okay, sir.
Mm. So these two techniques will be used in real life examples also, and the most efficient will be considered. So like this, we can use these two techniques for finding the path to the goal, which will be having the least cost. So based upon that, the best technique will be used. So different applications are there for these two techniques. So whichever is the best, it is used for that particular application. Any more question? So in the next class, we will see the game playing, these techniques of game 3. Till now, if you're having any question, you can ask.
So while determining the root node for heuristic, uh, how do we consider it? Anyone can be the root node?
Yeah, here only directly Arad is taking. Any rule is not considered here. Directly we are taking this no node only.
Okay, sir.
Yeah. Whatever we have discussed today, I will share something I've written. I will share after this class. Okay. So any question? Then we will see the next topic in the next class. After completing all this, we will come to see the applications. Using Python, we will see examples. We'll try to solve them. Okay, then for today, we are concluding here. Next, in the next class, we will see the other technique. Okay, then bye everyone.